Welcome to the Explainer. I am thrilled you're here. Today, we're setting up the foundation for all geometric reasoning. When we study geometry, we aren't just drawing pictures or making rough sketches. We're actually building a rigorous logical system from the ground up, using the absolute foundational building blocks of the discipline. Everything we construct, measure, and prove moving forward depends entirely on the ideas we're going to cover right here, right now. Okay, let's dive into this. We've got 5 distinct but intimately linked ideas on the agenda today. Points, lines, and planes. Mapping them on the coordinate plane, calculating distance and midpoint, proving congruence, and finally, constructions, conjectures, and proof. Here is our learning target for the day. By the time we wrap up, you'll be able to use precise geometric language and coordinate reasoning to describe points, lines, planes, distance, midpoint, and congruence. And ultimately, you'll be able to explain exactly why a geometric claim needs hard evidence or a formal proof, rather than just trusting what your eyes see. Let's kick things off with Section 1, Points, Lines, and Planes. All of geometry literally starts with these undefined abstract notions. Now, what's really fascinating here is how we classify these elements by their dimensions. Think about it. A point is zero-dimensional. It has literally no size whatsoever, just a location. A line is one-dimensional, with infinite length, and a plane is two-dimensional. If you've ever used dynamic geometry software, like GeoGebra, you've probably noticed that these are the absolute foundational tools. You always have to plot a point or define a line before you can really do anything else. Let's break down this precise mathematical language. A point isn't just a random dot. It is a precise location in space. A line is a straight, continuous path that goes on infinitely in both directions. Now, if you just take a piece of that line and give it 2 endpoints, you get a segment. Put multiple segments together to make a closed figure, and boom, you have a polygon. Software tools rely on these exact, strict definitions to create accurate visual representations. Without them, you're just sketching. Moving on to Section 2, the coordinate plane. This is where we take those abstract points we just talked about and give them a precise home by dropping them onto a grid. Enter the Cartesian grid. When you take 2 perpendicular number lines, your x-axis and your y-axis, and intersect them at a 0 point called the origin, you create a coordinate system. This is the exact moment where geometric points seamlessly align with algebra. And this brilliantly illustrates how we locate literally anything on that grid. We use an ordered pair, x, y. That first number tells us the horizontal distance from the origin, and the second tells us the vertical distance. The crucial takeaway here is that ordered pairs translate spatial relationships into exact mathematical values. We are turning shapes into calculable data. Let's move to Section 3 and see how this builds. With our points now sitting safely as data on a coordinate plane, we can measure exactly how far apart they are and where their exact mathematical center lies. Take the midpoint, for example. By definition, a midpoint is the exact middle point of a line segment, meaning it's perfectly equidistant from both endpoints. Because we're working on the coordinate plane, this isn't some guessing game. It's a measurable relationship derived directly from averaging the x and y coordinates. Let's walk through this calculation step by step to see how coordinate reasoning works in practice. Let's say we have a segment with endpoints at 2, 4, and 8, 10. Step 1, we average the x coordinates. 2 plus 8 is 10. Divided by 2 gives us 5. Step 2, average the y coordinates. 4 plus 10 is 14. Divided by 2 is 7. So our result, a precise midpoint sitting exactly at 5, 7. But hey, in geometry, we don't just calculate, we verify. We can check our work by confirming the midpoint is perfectly equidistant from both original endpoints. Look at the x values. 5 is exactly 3 units away from 2 and 3 units away from 8. Now look at the y values. 7 is exactly 3 units away from 4 and 3 units away from 10. It is a perfect calculable balance. Time for a quick check for understanding. If someone hands you a midpoint statement for a segment, how do you know if it's mathematically correct? Well, the analytical reasoning is this. Coordinate arithmetic proves a midpoint is correct only if the horizontal x distance and the vertical y distance from the center to both endpoints are perfectly equal. If they don't match exactly, it's simply not the midpoint. So the crucial point is that measurement requires exactness. And that brings us to Section 4. Congruence in geometry, where we shift our focus to comparing entire shapes. When we say two shapes are congruent in formal geometry, we don't just mean they kind of look the same. Congruence has a highly specific definition. Two figures match perfectly in size and shape because one can be mapped exactly onto the other using rigid motions. We're talking about transformations like rotating, reflecting across a line, or translating by sliding that perfectly preserve every single distance and angle.
Because these rigid motions preserve side lengths and angle measures, they form the bedrock for how we prove shapes are identical. This validates standard congruence criteria you'll be using, like angle, side, side, and side, side, side. These criteria let us evaluate polygons and solve problems without having to painstakingly measure every single part of a shape.
This leads us seamlessly right into our final section: constructions, conjectures, and proof. This is the ultimate cognitive leap required in high school geometry, moving from simple observation to concrete justification.
When we do a formal geometric construction, we rely on precise tools, like a traditional compass and straight edge or dynamic software. We are creating figures based strictly on the mathematical definitions we've talked about today. No estimations allowed. Because constructions use these strict mathematical rules, they guide us to observe patterns and make logical conjectures about how shapes will behave. But here is probably the most important takeaway of this entire explainer. Just look at the comparison here. On the left side, we have observation. A diagram might visually appear to show equal angles or parallel lines. That's evidence, sure. But on the right, we have logical proof. A proof is a rigorous argument using axioms, definitions, and theorems. Observing that a diagram looks a certain way is merely visual evidence. A proof is the only thing that guarantees a claim is actually true. Let's do one more check for understanding. If you see a diagram showing two triangles that look completely identical, does that diagram alone prove the two figures are congruent? The strict analytical answer is no, absolutely not. A diagram is never enough. It's just visual evidence. To mathematically prove it, you must explicitly state the reasoning, whether that's defining the specific rigid motions, using coordinate formulas, or applying a congruence theorem like side, side, side. To wrap things up, here is your quick recap. We built geometry from abstract points and lines to precise locations on the coordinate plane. We measured distances and midpoints using coordinate arithmetic and defined congruence through rigid transformations. Finally, we learned that visual observations are only evidence, while mathematical definitions and logic are required for absolute proof. So I want to leave you with this transfer challenge. Moving forward, how would you use the coordinate reasoning and definitions we discussed today to explain a brand new geometric relationship in an unfamiliar diagram? Think about that as you continue your journey into geometry. Thanks for watching.